So another lecture that's very important, we're going to look at Newton's second law of motion. This is arguably the most important of Newton's laws of motion. So when a constant unbalanced force acts on an object, it seems reasonable that the object will not have a constant velocity but will accelerate. But this raises a couple of questions. The first is, how does the acceleration of the object depend on the resultant force acting on it? And the second, can this relationship be expressed in a single equation? So the variables that are involved would essentially be the force applied, the mass of the object, and how fast it would accelerate. So let's picture this using what's used on this slide here, where we have an image of some boxes on top of a sled which is on an icy surface to reduce friction. In the first scenario, you push as hard as you can, and the sled starts from rest and attains a high velocity in a very little time. In scenario B, you push with less force on the sled, and the velocity increases more gradually. So it would seem to be that the acceleration increases as the net force increases. So basically, the more force you apply, the more acceleration you have. So what you see there is acceleration is proportional to F. So A is proportional to F. That's what that little symbol means. Now, let's say we applied a constant force and we had two different masses. So in scenario C, we have just one small box on top of the sled, and we apply a force, and we have a lot of acceleration. When we increase the boxes on the sled and we apply the same force, we have less acceleration. So here we can see that the acceleration decreases as the mass increases, or acceleration is inversely proportional to the mass. So Newton's second law is summarized like this. If the net external force on an object is not zero, the object will accelerate in the direction of the net force. The magnitude of the acceleration is directly proportional to the magnitude of the net force and is inversely proportional to the mass of the object. And we can turn that into an equation. When we put those together, we see that acceleration is proportional to the net force. Acceleration is inversely proportional to the mass. So if we multiply the net force by the mass, we end up having acceleration is proportional to the force divided by the mass. And we can rearrange that to F equals ma, which is the equation representation of Newton's second law of motion, where we have m being the mass, a being the acceleration, and F, of course, being the force, or F net being the resultant force. When we have F net equaling 0, it's possible we still might have motion, but the motion would be uniform. So if F net is 0, there could be something could be still traveling at a constant velocity, or it could have a 0 velocity. But whenever F net is not 0, we are definitely experiencing non-uniform motion. We have some sort of acceleration happening. For the first practice problem, it says here, for each of the following, determine the net force and then state whether the object is experiencing uniform or non-uniform motion. So we'll talk about these ones here. First, we have 5 Newton force directed north and a 3 Newton force directed south. If you add those forces together, you end up with 2 newtons north. That is non-uniform because we now have a net force that is not 0. And again, adding those together, 5 north plus 3 south is the same as 5 north minus 3 north, which is 2 newtons north. Another question. We have a number of different forces, and let's look at the vertical components and see what they add to first. So we have 4 north, then we have 1 south, so now we would have 3 north, and we have 3 south, which 3 north plus 3 south would be 0. Let's look at the east and west directions. 2 east plus 1 east plus 3 west, that adds up to 0. So again, we have a net force of 0, meaning that we have uniform motion. If the object had a constant velocity, it would continue moving at that constant velocity. If the object was not moving, it would continue to not be moving. Another one here, we have 2 east plus 4 west. Well, 4 west, if we take that as positive and the 2 east as negative, we would end up with positive 2 as our solution, and that would be 2.0 newtons west. That would be non-uniform motion. So what you see on this slide is something worth copying down as well. On the right side, we have a kind of a diagram here to help you solve problems that involve dynamics with the second law of motion. To solve a problem, typically you'll be given some sort of value that you need to solve for. And let's say your question asked you to solve for V, D, or T. Well, that shows up at the bottom of this chart. Let's say in your problem, you're given a number of different forces and the mass. So you would have to start with a free body diagram to first determine what the net force would be. Then you can use F equals ma to determine what the acceleration is. And then with the acceleration, you can use the other Newtonian equations of motion to determine the missing variable v, d, or t. Another way that this could work, let's say you're given v, d, and t, and you're asked to find the force applied on an object, but you're given some forces, but not the total resultant force. Well, if you have v, d, and t, you can solve for A. Once you know the acceleration, if you have the mass, you can solve for F net. And if we have our net force, our resultant force, we can go back to the free body diagram and find out what the missing force value would be. So this little chart helps you determine how to solve certain problems. You start in any one of those 4 rectangles, the free body diagram, F net, A, or VDT. And you can move between those rectangles using F equals ma, a free body diagram, or the non-uniform motion formulas. Problem 2 says a worker applies a force of 360 newtons east on a trunk of mass 50 kilograms with a frictional resistance that amounts to 340 newtons. So we were asked to draw a free body diagram of this situation. Let me move it so that we can see the problem at the top. Okay, so let's start with a box to show the object, and we're asked to, see if I can get this to, we're asked to draw the free body diagram if he's applying a force to the east, so we'll write 360 newtons. That'll be our east direction. The frictional resistance is 340 newtons. That's our free body diagram here. We also have the FG and the FN. In this case, we don't need to calculate them because we know that they're going to balance out. We're asked to find the acceleration of the trunk. So we say F equals ma, but F is really our F net. So that's 360 minus 340. And our M is 50. So that is going to be 20 over 50. And our acceleration works out to 0.40 meters per second squared, directed to the east. Let's pull up another problem here. A boy pushes on a 10 kilogram wagon, and the wagon accelerates at 2.5 meters per second squared. If the total frictional forces are 50 newtons, what must be the force exerted on it? So we're not asked to draw a free body diagram in this situation, but it's good to do so. So let's draw this free body diagram. We know that there's a frictional force of 50. There must be some applied force. There's an Fg and an Fn. There is a frictional force is always opposing, so there is motion. Sometimes in a free body diagram you would include the acceleration. It's not common that you would do that, but if it helps you understand it, we can do that in this case. So we know acceleration is happening in the right because we've chosen FA to be directed to the right. The question again asks, what is this force? So we have to find that FA. And we're given enough information. We know F net equals MA. And we know F net is equal to FA minus 50 in this case. So FA is MA plus 50. M is 10, A is 2.5. So FA would be 25 plus 50. It's going to be 75 newtons. And they haven't specified any sort of directions. So it would be acceptable to leave that without a direction. I think here it says forward, but we don't necessarily need to say that. It's sort of implied. Question number 4 says there's a mass of 15 kilograms. It rests on a frictional horizontal plane and is acted upon by a horizontal force of 30 newtons. What will be its velocity after 10 seconds? So now this is a situation where we're asked to find velocity. Velocity, of course, if you remember that chart we had, we can start with a free body diagram. We would then have to find an F net, use that to find our A, and then finally to find our velocity. We don't necessarily need the free body diagram because we know the F net already. So we know 30 is our F net. So let's write down F net equals MA. We would need to find acceleration in this case. So A equals F net over M. And A would be, F net is 30 over 15. So 2.0 meters per second squared. But we're not asked to find that. We're asked to find the velocity after 10 seconds. So we're looking for a VF. So it says the object rests. So we now know VI is 0. So the equation we should use is VF equals VI plus AT. And we're looking for VF. VI is 0, so we can just write down AT. VF equals 2.0 times 10. So VF is 20 meters per second. That's our solution. Now, the last problem. We have a car traveling at, it says this car is traveling at 28 meters per second. It applies its brakes. The car comes to a stop in 3.5 seconds. The mass of the car and the driver is 1.20 times 10 to the power of 3, so that would be 1,200 kilograms. What is the magnitude of the force of friction being applied by the brakes? So, first thing we need to do, we're kind of doing the opposite. We have the VDT information. We have to use that to find the acceleration, and then find our F net. We don't need to find the FBD because there is only one force being applied here. So, given the time, the VI, and the VF, knowing VF is 0, how do we find our A? Well, we can use the same equation we used last time. VF equals VI plus AT. And rearrange this for A, but knowing that VF is 0, that means that this would become negative VI over T. A is going to be negative in this case. Negative 28 over 3.5. That is something that I'm going to need to calculate. 28 divided by 3.5 is 8. And it's going to be negative 8.0 meters per second squared. Now we can use that to find our force. F equals MA. F equals M, which is 1200. A, which is negative 8.0. And I'll just calculate that here as well, times 1200. It's going to be negative 9,600 newtons. That's the force applied by the brakes. Note that it is negative because we are slowing down the vehicle to a stop.